AMD just did something nobody expected. In the one area, Nvidia has spent years telling you they dominate. An AMD GPU just beat them with ray tracing turned on in a real game. This video isn't about brand loyalty or cherry-picked benchmarks. It's about why that happened, what AMD actually changed, and what this moment exposes about ray tracing as a technology. By the end of this video, you'll understand why ray tracing has never worked the way it was marketed, and whether any of it is actually worth the massive performance hit you pay every time you turn it on. And to understand how we got here, we need to go back to the very beginning, to the moment ray tracing was first sold as the future of gaming. The ray tracing promise and the lie we bought. When ray tracing first entered gaming, it wasn't introduced as just another graphics option. It was sold as a turning point. Back in 2018, Nvidia stood on stage and framed ray tracing as the future of how games would look: real light, real reflections, real shadows. Not tricks, not shortcuts. Actual simulation of how light behaves in the real world. And on the surface, it was convincing. The demos looked unreal. Shiny cars reflecting entire city blocks, neon signs bouncing perfectly off wet pavement, glass and mirrors behaving exactly the way your brain expects them to. It felt like the final step toward photorealism. But here's the part most people didn't realize. Those demos weren't showing how ray tracing would actually be used in games. They were showing what ray tracing could look like if performance didn't matter. Real games don't exist in a vacuum. They have fast camera movement, explosions, dozens of dynamic light sources, and players who don't want to play at 30 frames per second. The moment ray tracing entered that environment, the promise started to fall apart. Because full ray tracing, the kind that simulates all the light in a scene, is brutally expensive. Even today, the fastest GPUs in the world still struggle to do it properly in real gameplay. So compromises were made. Instead of ray tracing everything, developers started using it selectively. Maybe reflections, but not shadows. Maybe global illumination, but at a lower resolution. Maybe only in specific areas where it looks good in screenshots. Ray tracing was technically on, but it wasn't whole. Games still relied heavily on baked lighting, screen space reflections, and traditional rendering tricks. Ray tracing wasn't replacing those systems, it was being layered on top of them, thinly and carefully, so performance wouldn't completely collapse. That's the part nobody explained. You were told ray tracing was the future. You weren't told it was already compromised. So, when AMD launched GPUs that didn't compete well in ray tracing, the narrative was easy. Nvidia was ahead. AMD was behind. End of story. But that framing ignored something important. AMD didn't hesitate on ray tracing because they didn't understand it. They hesitated because they saw the cost. They saw how much performance it destroyed, how unstable the results could be in motion, and how even Nvidia was already relying on clever workarounds to keep it usable. Behind the scenes, ray tracing was struggling far more than marketing let on, and that struggle forced both companies into a corner. Either brute force ray tracing and accept massive performance losses, or start faking the results intelligently and hope most people wouldn't notice. That fork in the road is what led us here, because once ray tracing couldn't scale on its own, the real battle stopped being about hardware and started being about reconstruction, denoising, and AI. And to understand why AMD and Nvidia ended up with such different solutions, we need to talk about the ugly technical reality that made those solutions necessary in the first place. Why ray tracing is so broken. At its core, ray tracing is simple to explain. Instead of faking how light behaves, the game casts rays into the scene and calculates how light realistically bounces, reflects, and scatters. The closer the simulation gets to real light behavior, the more realistic the image becomes. The problem is that realism comes at an enormous computational cost. Every ray requires processing power, and accurate lighting requires many rays per pixel per frame. When you scale that up to modern resolutions, the math becomes brutal. A 4K image contains over 8 million pixels, and at 60 frames per second, that means hundreds of millions of pixels are being processed every second. When each of those pixels needs multiple rays to look correct, full ray tracing quickly becomes impossible to run in real time, even on today's most powerful GPUs. Because of that, modern games do not trace all the light in a scene. Instead, they trace as little as possible to maintain playable performance. Rays are cast at lower resolutions, fewer rays are used per pixel, and only select effects like reflections or shadows are ray traced instead of full global illumination. While this keeps frame rates from collapsing, it creates a new problem. the ray-traced image is incomplete. When too few rays are cast, large portions of the image contain missing information. This shows up as visual noise, shimmering reflections, unstable shadows, and flickering light when the camera moves. The raw output of ray tracing under these conditions is not something players would accept, which is why it is almost never shown on its own. To compensate, developers rely heavily on denoisers. These algorithms attempt to clean up the noise by smoothing the image and reusing information from previous frames. Instead of generating new detail, denoisers estimate what the image should look like based on limited data. When everything lines up, the results can look surprisingly good. When it doesn't, the image begins to smear, ghost, or lose fine detail, especially in motion. This is why ray tracing often looks impressive in still screenshots, but breaks down during gameplay. The system is constantly guessing, correcting, and recorrecting the image as the camera moves. Unlike traditional graphics settings, ray tracing does not degrade gracefully. Lower the quality too much, and the image does not simply lose detail, it becomes unstable. At that point, there are only two options. Either brute force the problem with massive amounts of hardware, or accept that ray tracing needs significant post-processing help to look acceptable. That reality is what pushed both Nvidia and AMD toward reconstruction and AI-based solutions. Because once denoising became mandatory, raw ray tracing performance stopped being the deciding factor. That is where the real problem begins, and why the fight between AMD and Nvidia stopped being about ray tracing itself and started being about who could hide its weaknesses better. The denoiser problem nobody talks about. Once ray tracing proved impossible to run cleanly on its own, denoisers stopped being a nice-to-have feature and became absolutely mandatory. Without them, the raw output of ray tracing is simply not usable in real-time games. The noise is overwhelming, reflections break apart, shadows flicker, and the image becomes so unstable that it would be immediately rejected by players. Every modern ray-traced game you've played relies on denoising just to function. The basic idea behind denoisers is straightforward. Because the game cannot afford to cast enough rays in a single frame, the denoiser pulls information from multiple frames over time and blends it together. One frame might be missing detail, but several frames combined can approximate what the image should look like. This process, known as temporal accumulation, is the foundation of modern ray tracing pipelines. The problem is that games are not static images. Cameras move constantly, characters animate, lights flicker, reflections shift, and explosions rewrite entire scenes in a split second. When that happens, the denoiser suddenly loses the reliable history it depends on. Instead of reconstructing detail, it starts guessing more aggressively, smoothing away noise at the cost of sharpness and accuracy. That's when you begin to notice smearing, ghosting, delayed reflections, and surfaces that seem to blur or melt when you move. This is why ray tracing behaves so differently depending on the type of game. In slow, cinematic experiences, denoisers have time to gather enough data to stabilize the image. In fast-paced shooters or competitive titles, the denoiser is constantly chasing a moving target. The image might look acceptable when you stand still, but the moment you start moving, quality collapses. Reflections lag behind reality, fine detail disappears, and lighting feels disconnected from what's actually happening on screen. What makes this worse is that most ray-traced games don't rely on a single denoiser. They rely on many. There's often one denoiser for reflections, another for shadows, another for global illumination, and sometimes additional passes layered on top. Each of these systems works independently, with its own assumptions and failure points. When everything lines up, the image holds together. When it doesn't, artifacts stack on top of artifacts, creating instability that no single setting can fully fix. This is the part that rarely gets explained to players. The final image you see is not a clean simulation of light. It is the result of multiple denoisers aggressively filtering, smoothing, and reconstructing incomplete data in real time. The more ray tracing effects a game uses, the more denoisers it needs, and the harder it becomes to maintain visual stability. Instead of ray tracing adding realism, it often introduces a layer of uncertainty that the system is constantly trying to hide. At a certain point, both Nvidia and AMD ran into the same wall. You can only stack so many denoisers on top of an incomplete signal before the entire pipeline starts to collapse under its own complexity. The problem wasn't just noise anymore. It was was the lack of a unified way to reconstruct the final image in a way that made sense for real gameplay. That realization forced a shift in strategy. If ray tracing was going to survive, denoising couldn't be treated as an afterthought. Reconstruction had to become smarter, more centralized, and more aware of the final image the player actually sees. That's the moment when ray tracing stopped being just a hardware problem and became an AI problem. And that's exactly where Nvidia made its move. Nvidia's solution: ray reconstruction. By the time Nvidia realized how much ray tracing depended on denoising, they also realized something else. The traditional approach wasn't going to scale. Stacking more denoisers on top of incomplete ray-traced data was only making the image more fragile, not more realistic. If ray tracing was going to work long-term, the entire reconstruction process needed to be rethought from the ground up. That's where Nvidia's idea came in. Instead of treating denoising and upscaling as separate steps, Nvidia decided to merge them. DLSS was already reconstructing detail from low-resolution images using machine learning, so Nvidia folded ray tracing cleanup into that same pipeline. Rather than using multiple specialized denoisers, they replaced them with a single AI model that could look at the entire image and decide how it should be reconstructed. This is what Nvidia calls ray reconstruction. The key difference is that ray reconstruction doesn't just try to clean up noise. It tries to rebuild the final image holistically. It looks at motion vectors, depth information, lighting data, and previous frames all at once, then uses AI to predict what the scene should look like at full quality. Instead of guessing blindly, it leverages patterns learned from vast amounts of training data. The result is immediately noticeable. Reflections resolve faster, fine detail holds together better in motion, grain and flicker are dramatically reduced. In many cases, the image looks sharper and more stable than what traditional denoisers could ever produce, even though the underlying ray tracing data is still low resolution. There's another important benefit too. Because ray reconstruction replaces multiple denoisers with one unified system, it can actually improve performance in some scenarios. Instead of running several expensive cleanup passes, the pipeline becomes more efficient. In practice, the performance cost is often surprisingly small compared to the visual improvement. But this approach comes with trade-offs. Ray reconstruction is tightly integrated with DLSS. You don't get to mix and match upscalers. If you want Nvidia's reconstruction, you have to use Nvidia's ecosystem. That means DLSS, Nvidia hardware, and Nvidia-supported games. If a game doesn't implement it, you're out of luck. And support is still limited. Even years after its introduction, ray reconstruction is only available in a small handful of titles. When it works extremely well. When it's not there, you're back to the same old denoising problems. Still, this was a major step forward. Nvidia didn't just try to brute force ray tracing with hardware. They accepted that reconstruction was unavoidable and leaned fully into AI as the solution. Whether you like the lock-in or not, ray reconstruction showed what was possible when denoising stopped being an afterthought. And if this breakdown is already helping you understand what's actually going on under the hood, this is a good moment to pause for half a second. If you appreciate clear explanations without marketing fluff, hit like and subscribe. It genuinely helps the channel, and it lets me keep doing deep dives like this instead of surface-level takes. Because Nvidia's move didn't just improve ray tracing, it forced AMD to respond. And AMD's response took a very different approach: AMD's surprise counterattack. When AMD first announced its answer to Nvidia's ray reconstruction, expectations were low. For years, AMD had been behind in ray tracing, and early demonstrations of their new approach did not inspire much confidence. The visuals looked rough, the messaging was unclear, and many people dismissed it as AMD simply trying to copy Nvidia without the same level of maturity or polish. That assumption turned out to be wrong. AMD's solution, called ray regeneration, wasn't designed to mirror Nvidia's approach. Instead of tightly coupling reconstruction to a single upscaler, AMD deliberately separated the process. Ray regeneration focuses on cleaning up ray-traced data itself, regardless of which upscaling method is being used. In theory, that means it can work alongside FSR, DLSS, Intel XeSS, or even traditional anti-aliasing. This design choice was intentional. AMD has consistently pushed for more open graphics ecosystems, and ray regeneration reflects that philosophy. Rather than building one monolithic system, AMD aimed to create a modular solution that developers could integrate without locking themselves into a single vendor's technology stack. Alongside ray regeneration, AMD introduced a broader umbrella they call FSR Redstone, which includes techniques like radiance caching, intended to make ray tracing more efficient overall. While not all of these features are fully deployed yet, they point toward AMD's long-term strategy: reduce the cost of ray tracing by being smarter about how and when rays are traced, rather than relying entirely on post-processing to fix the damage afterward. At first glance, ray regeneration seems like a disadvantage compared to Nvidia's approach. Because it is decoupled from the upscaler, it doesn't benefit from the same compounded efficiencies that DLSS provides. Nvidia's system can reconstruct detail and denoise in a single pass, while AMD's solution operates as an additional step in the pipeline. However, that separation also creates a different set of strengths. Ray regeneration tends to respond faster in motion. In scenes with rapid lighting changes, flashing effects, or quick camera movement, it can resolve changes more quickly than traditional denoisers. Instead of slowly accumulating data over time, it reacts more immediately to what's happening on screen. In fast-paced games, that difference matters. This is where AMD's approach starts to make sense. They weren't trying to win screenshot comparisons. They were trying to improve how ray tracing behaves during actual gameplay, where stability and responsiveness matter more than perfect still frames. Of course, this also means accepting compromises. Ray regeneration doesn't always resolve fine detail as cleanly as Nvidia's ray reconstruction, especially in static scenes. It can introduce artifacts like light leaking or uneven smoothing, and its performance cost can be higher because it runs independently of the upscaler. But AMD wasn't chasing perfection. They were chasing usability. And that philosophy sets up the most important question of all. When these two approaches finally collide head-to-head, which one actually holds up better in real games? That's where things get interesting. Ray regeneration versus ray reconstruction. When you put AMD's ray regeneration and Nvidia's ray reconstruction side by side, the first thing you notice is that they fail in very different ways. This isn't a simple case of one looking good and the other looking bad. It's a trade-off between stability, detail, and how the image behaves when the game is actually moving. In static scenes, Nvidia's ray reconstruction usually has the upper hand. Fine details and reflections resolve more clearly, surfaces look more defined, and the image feels cleaner overall. When nothing is changing quickly, the AI model has time to analyze motion data, depth information, and lighting history, then reconstruct a very convincing final image. This is why DLSS ray reconstruction tends to win in still comparisons and slow camera pans. AMD's ray regeneration struggles more in those situations. Static reflections can look slightly softer, and in some scenes, the reconstruction can feel uneven. You may notice subtle light leaking, splotchiness, or areas where the lighting feels less anchored to the environment. These issues are not constant, but when they appear, they are more noticeable than the artifacts produced by Nvidia's solution. Where the balance shifts is in motion. In fast-moving scenes, especially in shooters or multiplayer games, ray regeneration often reacts faster than Nvidia's approach. Lighting changes resolve more immediately, reflections update with less delay, and sudden flashes of light don't linger or smear across multiple frames. The image may not be as sharp frame by frame, but it feels more responsive and less temporally unstable. Ray reconstruction, by contrast, can sometimes feel overly conservative in motion. Because it relies so heavily on accumulated data, it occasionally prioritizes stability over immediacy. This can result in reflections or lighting effects that take an extra moment to catch up when the scene changes rapidly. In isolation, this isn't a deal breaker, but in fast gameplay, it becomes noticeable. Another important difference is how each system handles failure. When ray reconstruction breaks down, it usually manifests as ghosting or delayed detail resolution. When ray regeneration breaks down, it tends to produce more visible artifacts, like light leaks or uneven smoothing. Neither is perfect, but they are different kinds of imperfections that affect how the image feels during play. Performance also plays a role here. Nvidia's integrated approach is generally more efficient because reconstruction and upscaling happen together. AMD's decoupled system often costs more performance, since ray regeneration runs as an additional step, regardless of which upscaler is being used. That performance hit can offset some of the gains in responsiveness, especially on weaker hardware. So the head-to-head result isn't a clean win. If you care most about image quality in slower, cinematic scenes, Nvidia's ray reconstruction usually looks better. If you care more about how ray tracing behaves during real gameplay, especially in motion, AMD's ray regeneration can feel less sluggish and more immediate. This is why the debate isn't settled by screenshots. Both companies are solving the same problem from opposite directions, and both are exposing the same uncomfortable truth. Ray tracing still isn't good enough to stand on its own. It has to be reconstructed, regenerated, and heavily assisted to function at all. And once you look at what this assistance costs in performance, the conversation shifts again. Because visual trade-offs are one thing, but the performance hit is where this entire idea starts to fall apart. The performance reality check. Once you stop looking at screenshots and start looking at frame rates, the entire ray tracing conversation changes. It doesn't matter which reconstruction method looks better if turning the feature on destroys performance to the point where the game no longer feels good to play. And that's exactly what happens. Even on high-end GPUs, enabling ray tracing comes with a brutal cost. In many cases, performance drops by 60 to 75% compared to running the same game without ray tracing. That isn't a small trade-off. That's the difference between smooth gameplay and something that feels sluggish or inconsistent. What surprises a lot of people is that this isn't just an AMD problem. Nvidia GPUs, despite being marketed as ray tracing champions, suffer almost the same proportional losses. Turn ray tracing on and frame rates collapse. Upscaling and frame generation can recover some of that performance, but they don't eliminate the underlying cost. They just hide it. This is where reconstruction techniques start to look less like enhancements and more like survival tools. Ray reconstruction and ray regeneration aren't making ray tracing cheap. They're making it barely usable. Without them, the performance hit would be even worse, and the visual noise would be unacceptable. In certain games, this reality becomes impossible to ignore. There are titles where AMD GPUs suddenly outperform Nvidia in ray tracing workloads, not because AMD has magically surpassed Nvidia in raw ray tracing hardware, but because of game-specific optimizations and partnerships. Call of Duty is a prime example. In those scenarios, AMD cards can pull ahead by a noticeable margin, even with ray tracing enabled. But this is where things get misleading. That advantage doesn't come from ray tracing itself. It comes from how the game is built, how the engine schedules work, and how aggressively reconstruction and denoising are applied. In most other ray trace titles, Nvidia still pulls ahead as ray tracing complexity increases. So while those wins are real, they don't represent a broader shift in ray tracing leadership. They highlight how fragile and situational ray tracing performance still is. And this is the uncomfortable takeaway. If ray tracing were truly ready, it wouldn't require massive upscaling, AI reconstruction, frame generation, and vendor-specific tricks just to stay playable. The fact that both AMD and Nvidia rely so heavily on these tools tells you everything you need to know about where the technology actually stands today. The moment you step away from flagship GPUs and look at mid-range hardware, this problem becomes even more obvious, because that's where the illusion completely breaks. Is ray tracing even worth it? This is the point where the entire ray tracing conversation collapses under its own weight. Once you move away from flagship GPUs and look at what most people are actually playing on, the trade-offs become impossible to ignore. On mid-range hardware, turning ray tracing on is less of a visual upgrade and more of a system shock. Frame rates don't just dip, they crater. Games that were comfortably running well over 100 frames per second suddenly struggle to maintain 40 or 50. And that's before you start stacking upscaling, frame generation, and reconstruction on top just to stay afloat. What makes this harder to justify is how subtle the benefits often are. In many real gameplay scenarios, especially in fast-paced or competitive games, the ray-traced effects are difficult to notice unless you're actively looking for them. Reflections might be more accurate, lighting might be slightly more realistic, but the moment-to-moment experience rarely changes in a way that feels worth losing half or more of your performance. In fact, when you turn ray tracing off entirely, many modern games still look excellent. Traditional lighting techniques have improved dramatically over the years, and in motion, they often provide a cleaner, more stable image than ray tracing struggling to reconstruct itself in real time. For most players, the visual difference does not justify the cost. This creates an uncomfortable question. If ray tracing requires massive performance sacrifices, aggressive upscaling, AI reconstruction, and frame generation just to function, is it actually improving games or just complicating them? Are we moving forward? Or are we stacking layers of technology to solve a problem that didn't exist for most players in the first place? That's the real takeaway from AMD and Nvidia's latest showdown. AMD didn't destroy Nvidia. Nvidia didn't suddenly lose its edge. What happened instead is that ray tracing was exposed for what it currently is, a feature that still depends on heavy assistance to be usable, and one that often asks far more than it gives back. If you're playing slow, cinematic single-player games, and you enjoy pushing visuals to the limit, ray tracing can absolutely add to the experience. But if you care about responsiveness, clarity in motion, and consistent performance, the smartest move for most players is still to turn it off. And that's not a failure on your part. That's the technology not being ready yet. If this breakdown helped you cut through the marketing and actually understand what's going on, take a second to hit like and subscribe. It helps the channel more than you might think, and it lets me keep making deep dives like this instead of surface-level takes. And now, I want to hear from you. Do you actually use ray tracing in the games you play? Or have you already decided it's not worth the trade-off? Drop your experience in the comments because this debate is far from over.